A seismic tremor recently rippled through the world of mathematics. But this wasn't caused by some arcane theory. It was caused by a simple, unassuming 13-sided shape. Nicknamed the hat, this single shape has solved a problem that has captivated mathematicians for over half a century: the quest for an Einstein tile. Now, this has nothing to do with the famous physicist. The name comes from the German words Einstein, meaning one stone. It's the story of a single, solitary shape that can tile an infinite plane without ever repeating its pattern. This breakthrough, spearheaded by a retired print technician, has not only answered a long-standing question, but has ignited a flurry of excitement in art, design, and even materials science. Today on G Fun Facts Online, we're telling the comprehensive story of the Einstein tile, a journey from a recreational curiosity to a profound mathematical revelation. To really get why the hat is such a big deal, we need to talk about tiling. For thousands of years, humans have been fascinated with tessellations, covering a flat surface with shapes, leaving no gaps and no overlaps. Think of the intricate mosaics in ancient Rome, or the mesmerizing patterns of Islamic art. For most of history, these tilings were periodic. That means they have a repeating pattern. Imagine a checkerboard or a honeycomb. If you shift the whole pattern a little bit, it lines up perfectly with itself. That property is called translational symmetry. It seemed like all tiling should work this way. In 1961, a logician named Hao Wang even conjectured that if you could tile a plane with a set of shapes, you must be able to do it in a repeating, periodic way. But just 3 years later, in 1964, Wang's own student, Robert Burger, proved him wrong. Burger found a set of tiles that could only tile the plane aperiodically, that is, in a pattern that never, ever repeats. This discovery was a landmark, but Burger's first set was a staggering 2,426 different tiles. The race was on to find smaller sets. By 1971, Raphael Robinson had whittled it down to just 6. Then, in the 1970s, the renowned mathematical physicist Sir Roger Penrose made a huge leap. He discovered sets that required only 2 tiles, famously known as kites and darts. These Penrose tilings became the most famous examples of aperiodic patterns, capturing the public's imagination. But one tantalizing question remained. Could a single tile, a monotile, do what Penrose's pairs did? Could one lone shape force a non-repeating pattern across an infinite plane? This became known as the Einstein problem, the search for the one stone. For decades, many believed it might be impossible. The answer didn't come from a university, but from the home of David Smith, a retired print technician from East Yorkshire, England. Smith, a self-described imaginative tinkerer of shapes, was playing with a software program in November 2022. He created a quirky 13-sided polygon that looked a bit like a fedora hat. As he tiled the shape on his computer, he saw something strange. The tiles fit together perfectly, but the pattern just didn't seem to repeat. Intrigued, he went offline, cutting dozens of these hats from cardboard. The more tiles he laid out by hand, the more convinced he was that he had found something special. Knowing he needed help to go further, Smith emailed Craig Kaplan, a computer science professor at the University of Waterloo in Canada. Kaplan was an expert in tiling theory, and he was immediately fascinated. He ran the hat shape through his own software, which could generate massive patches of tiling. The program tiled ring after ring of hats, and just as Smith suspected, the pattern never repeated. Kaplan knew they were onto something huge, but they needed a rigorous mathematical proof. He assembled a dream team, which they called the Hat Pack. He brought in Chaim Goodman-Strauss from the University of Arkansas, a veteran of tiling theory. Goodman-Strauss, in turn, recommended their secret weapon, Joseph Samuel Myers, a software developer from Cambridge with a PhD in combinatorics. The collaboration was a perfect fusion of skills. Smith had the initial insight and hands-on intuition. Kaplan had the computational power to explore the tile at a massive scale. Goodman-Strauss provided the deep theoretical knowledge, and Myers brought his exceptional analytical skills to craft the proof. In a remarkably short time, just over a week after joining the team, Myers delivered the first of 2 proofs, showing the hat was truly aperiodic. The team published their findings in a paper called An Aperiodic Monotile in March 2023, and the math world went wild. So how did they prove it? The team actually presented 2 different proofs. The first was more traditional. Myers showed that the hat tiles could assemble into larger composite shapes, which he called metatiles. These metatiles could then be arranged to form even larger supertiles, and so on, in a never-ending hierarchy. This kind of hierarchical structure is a known feature of aperiodic tilings. The proof, which was computer-assisted, showed that any tiling with hats had to follow this structure, which by its very nature prevents a repeating pattern. The second proof was even more elegant, something Kaplan called a mathematical rabbit out of a hat. This came from another surprising discovery by Smith, a second aperiodic monotile he nicknamed the turtle. Myers realized the hat and the turtle were part of an infinite family of related shapes. Imagine a slider that could continuously morph the hat into the turtle by adjusting the lengths of its sides. At the 2 extremes of this slider, the shapes could actually tile the plane periodically. Myers cleverly used the geometry of these simple periodic cases to prove that all the shapes in between, including the original hat, could only tile the plane aperiodically. It was a brand new technique for the field. The discovery of the hat was monumental, but there was one small catch. To tile the plane, you needed to use both the original hat shape and its mirror image. This left a question open. Could a single shape force a periodicity using only rotations and slides without flipping it over? Once again, David Smith found the answer. Soon after their paper was published, he identified another shape in their new family of tiles. They named it the specter. The specter had a unique property. If you used both the tile and its reflection, you could make a repeating pattern. But if you used only one version, either the left-handed or the right-handed specter, it could only tile the plane aperiodically. This is called chiral aperiodicity. To make it perfect, the team made a tiny refinement. They curved the edges of the specter slightly. This simple change made it impossible for the tile to fit together with its mirror image. The result was a strictly chiral, aperiodic monotile. A single shape, without any reflections, that forces a non-repeating pattern. It was the definitive and elegant answer to the Einstein problem. So, beyond being a cool math puzzle, what does this mean for the real world? One of the most significant connections is to materials science, specifically to quasicrystals. Discovered in 1982 by Dan Shechtman, who won a Nobel Prize for it. Quasicrystals are materials whose atoms are arranged in an ordered but non-repeating pattern, just like our aperiodic tilings. The hat and specter provide new mathematical models to understand these bizarre materials. Scientists can now explore how the properties of these tiles might translate into physical materials. Quasicrystals are already known for being incredibly strong, having low friction, and resisting heat. These new tile patterns could help us design new materials with specific properties for aerospace, electronics, and other advanced tech. Of course, the aesthetic appeal was instant. The discovery sparked a wave of creativity. People started making quilts, cookies, 3D printed tiles, and digital art based on the patterns. The National Museum of Mathematics even held a contest for the most creative uses. In architecture, these tiles could be used to create stunning, unique mosaics for floors, walls, and facades, offering a beautiful alternative to the repetitive patterns we see everywhere. Beyond the math and the applications, the story of the Einstein tile is a powerful story about people. It's a story of how a passionate amateur, David Smith, driven by pure curiosity, solved a problem that had stumped professionals for decades. It also highlights the incredible power of collaboration. A retired technician, a computer scientist, a mathematician, and a software developer came together, and their combined expertise made the breakthrough possible. This discovery is not the end of the story. It's the beginning of a new chapter. The researchers believe that now that the door is open, other Einstein tiles are just waiting to be found. Questions remain. What exactly is the special sauce that makes these tiles work? Can we find even more surprising connections between pure math and the physical world? The quest for the Einstein tile has been a long and fascinating journey, reminding us that fundamental discoveries can still be made, often in the most unexpected places, by the most unexpected people. The legacy of the hat and the specter will inspire a new generation to keep exploring the infinite, beautiful complexity of shapes